We don't understand the world right now. Those are not my words. Those are the words of Adam Rees, a scientist at Johns Hopkins University who won the Nobel Prize, a man whose job it is to measure how fast the universe is expanding. He's not being dramatic either. From what he's reading, it's clear that something in our picture of reality doesn't make sense. Cosmology has been based on a single elegant premise for almost 100 years. The normal model is what we call it, and formula and assumptions that explain everything from the very beginning, just a few hundredths of a second after the Big Bang. It has worked perfectly for decades, answering observation after observation with a level of accuracy that seems almost too good to be true. The James Webb Space Telescope then went live. What Webb found did not back up what we already knew. It made things harder. In some cases, it went against it. The cracks have gotten bigger as we've looked deeper with this lens. It all starts with a number. This number tells us how fast the universe is growing right now. It's called the Hubble constant. That is, neither in the past nor in some made-up future. Today, right now, you might think that number would be easy to pin down. 2 ways, 2 teams, the same world, and the same answer. That's the way science should work. It wasn't. It's happened before. Since Edwin Hubble first estimated it in the 1920s, the Hubble constant has been a source of disagreement. He was way off with his first guess, which made the universe look younger than Earth. After that, 2 groups of astronomers fought like hell for decades over whether the real number was closer to 50 or 100, a fight so bad that it split the field in half. By the beginning of the 2000s, the number had finally come together. It was around 70, give or take, according to everyone. There was no more war. The issue with measurements was fixed, except that it wasn't. As the instruments got better, a new split showed up, not as big as the old one, but much more stubborn. The first way looks very, very far back. The Planck satellite from the European Space Agency studied the cosmic microwave background for about 4.5 years. This is the faint glow of radiation that was left over from when the universe was about 380,000 years old. Scientists used that map to figure out what the early universe was like, put that information into the standard model, and then ran the equations forward almost 14 billion years to figure out how fast the universe should be growing now. They were told that it was about 67 kilometers per second per megapark. By the way, a megapark is 3.26 million light years across. When you look out into space, galaxies are moving away from us 67 kilometers per second, faster for every 3.26 million light years. Clean number, very little room for error, and a trust level through the roof. The second way is easier to understand. In place of studying the past and making predictions about the future, it checks out the present. The cosmic distance ladder is a method that Adam Rees and his group called SH0ES use. First, they figure out how far away close stars called Cepheid variables are that are pulsing. Stars whose brightness changes at a rate that is directly related to how bright they are. To find the distance, you need to measure the pulse, figure out how bright it really is, and then compare it to how bright the star looks from Earth. As they move farther away, they reach galaxies that have both Cepheids and a type of star explosion called a Type 1a supernova. It's helpful that all of these supernovae burst with about the same brightness peak. Once they are aligned with Cepheid in the same galaxy, you can find them in galaxies hundreds of millions of light years away and figure out how far away those galaxies are. The Hubble constant is found by adding that number to the speed at which they are moving away. The Rees team got 73, not 67, which is 73.6 kilometers per second per megapark, faster than what the normal model says should happen. It sounds like there was a rounding mistake. It's not. In an area where measurements are usually accurate to within 1%, an 8 to 9% difference between 2 separate methods is very big. One could be more than 1 billion years younger than the one we see now, which is about 13.8 billion years old. It changes the size of the universe that we can see. It changes how fast galaxies are moving apart. It might change the kind of dark energy that has been pulling everything apart since the late 1990s. Take a moment to think about what that means. If the universe is growing faster than our best model says it will, then everything that depends on that model changes. The world is getting younger. There are different distances between galaxy groups. When did the first stars form? When did the first heavy elements form inside dying suns? And when did the conditions for planets, chemistry, and finally life become possible? Everything moves. You're not just turning a handle on the panel. You are changing the whole history of everything that has ever happened. Scientists thought for a while that someone had messed up. Stellar crowding was the most common idea. Cepheid variables usually live in the dusty, thick disks of galaxies that aren't very old. Hubble's cameras sometimes mixed the light of close stars with that of the Cepheid, making them look brighter than they really were. When Cepheid is brighter, distances are estimated to be shorter. When distances are smaller, the Hubble constant is bigger. The idea went that things would calm down if you could fix that blending. These stars were seen by Reese with the James Webb Space Telescope. Webb goes around the Sun about 1.5 million kilometers away from Earth, far enough that the Earth's atmosphere and heat rays can't affect it. Its 6.5-meter gold-plated mirror picks up infrared light so well that it makes Hubble look like a pair of reading glasses. This could be solved by Webb if there was one. Many people in the field thought that Webb would slightly ease the tension, that its sharper vision would show the blending, fix the distances, and bring the Hubble constant back in line with the standard model. Before the data came in, some scientists were already writing the funeral leaf for the crisis. The infrared cameras on Webb can see through dust and crowds more clearly than Hubble ever could. There would be no problem with blending if sight showed it. Webb's eyes would make the Cepheid look less bright. It would take longer for things to move, and the Hubble constant would go back down to 67. There was no crisis. It didn't happen that way. Webb proved Hubble's numbers. Not pretty close, but pretty close. The Cepheid looked the same. The distances were there. The rate of growth stayed at 73. The SH0ES team published a paper in the astrophysical journal Letters in early 2024, saying that they had completed all of Hubble's Cepheid observations, linking 1,000 Cepheids across 5 host galaxies and 8 supernovae. The Webb reached a galaxy called NGC5468, which is about 130 million light-years from Earth. There was no doubt about the outcome. There was a very high chance that the measurements were wrong. That's how Reese put it. Now that the mistakes have been found and fixed, the only thing that could be wrong is our understanding of the world. David Gross, winner of the Nobel Prize in particle physics, was asked by Reese at a 2019 meeting at the Kavli Institute for Theoretical Physics in California if this difference should be called a problem in the field. Gross pushed him back. He told them not to call it a problem or a conflict. It is a problem, they should call it. The situation got worse by December 2024. The Reese team released their biggest Webb study yet, which was based on data from the telescope's first 2 years of use. To find out how far away supernova host galaxies were, they used 3 different methods. One was to compare spheroids to stars that are rich in carbon, and the other was a method called the tip of the red giant branch. All 3 methods agreed with the readings that Hubble made the first time. All 3 pointed to a universe that is growing faster than the normal model lets it. Either the model is wrong, or there is something in the physics that we haven't thought of. Some people don't even think the stress is real. An astronomer at the University of Chicago named Wendy Friedman has spent years making a separate distance path that depends less on Cepheids. Her team also uses red giants in a class of stars called JAGB. These stars are found in less crowded parts of galaxies and are less likely to be affected by dust and mixing. In August 2024, when she turned in her own Webb study, the results from her 3 different methods were not the same. The usual model said that the red giant and JAGB methods should have landed between 68 and 70. The reading of her CFID was higher, close to 72, but there were more unknowns. The total number of people she found was about 70, spread out between the two camps. Nobel Prize-winning cosmologist Saul Perlmutter at UC Berkeley looked over Wendy Friedman's data before it was made public. He said that the results show there may be a tension in the measurements made from stars alone before they are even compared to the cosmic microwave background. That's not the same thing. It means that the distance ladder, which scientists have used for 100 years to make maps of the nearby universe, may have problems that can't be fixed by a single telescope. Rees pushed back. He said that Wendy Friedman's team had only looked at a small group of supernovae, which might not be a good representation of all of them, which could have skewed the results in a bad way. Today, the argument between these two groups is one of the most closely watched rivalries in the field of physics. Each team is smart and careful, and they both look up at the sky and come to different opinions about what it means. Early dark energy is a theory that keeps coming up, a made-up burst of extra growth that happened in the few 100,000 years after the Big Bang and then went away. What if that happened? It would change the early universe just enough to move the Planck forecast closer to 73 without changing any of the other things that the standard model gets right. Mark Kamiankowski, a cosmologist at Johns Hopkins who helped come up with this idea, says, "It's like the world getting a surprise kick right after it was born." There would have been a small push that would have been felt through 14 billion years of growth, slightly changing the rate we use today. Early dark energy might be real, but no one knows for sure. It is one of the few ideas that could solve the Hubble strain without destroying everything that works. But no one has found it yet. The stress would be enough by itself. But Webb hit back with a second blow. Almost as soon as the telescope began to look, it found galaxies in the early universe that shouldn't have been there. Not small, dim, young galaxies. As the standard model said, they would be at those distances. A lot of them. Galaxies were seen because they were formed only 500 to 700 million years after the Big Bang. Some of them are as big as the Milky Way. It looks like a galaxy that took about 13 billion years to form, put itself together in less than a billion years. An astronomer at the University of Texas at Austin named Michael Boylan Colchin did the math for a paper that was published in Nature Astronomy. He showed that 6 of the oldest and heaviest galaxy candidates that Webb saw were very close to the edge of what the standard model can explain. For galaxies to get that heavy so quickly, almost every atom in the dark matter halos around them would have had to turn into a star. That transfer rate would be around 10% in a perfect world. The gas never turns into anything 90% of the time. Either it's too hot, radiation blows it away, or it just moves around. There doesn't seem to be any waste in these galaxies. It's like a machine that uses every scrap of raw material to make a finished product. That's not how physics works. Not in any model that was made. The first response was, to be honest, alarm. If galaxies this big really did form this quickly, then either our models of how galaxies form are very incomplete or the standard model of astronomy needs to be changed. Some scientists think that there may have been new particles or forces in the early universe that sped up the formation of stars more than what current models can explain. After that, there was an error. Katherine Chworowski, a graduate student at the University of Texas, led a study that looked at the data again and came out in the middle of 2024. She found that many of the galaxies that seemed too big were actually just fooled by their own black holes. Because of their small size and bright color, these galaxies were called little red dots. They were home to black holes that were quickly eating gas. All that dropping stuff caused a lot of friction, which heated it up very quickly. And that heat sent a lot of light out into the universe, mixing with the light from the stars. Webb's cameras show that a galaxy with a hungry black hole in the middle of it looks a lot like a galaxy with 10 times as many stars up close. Brightness is what the viewer sees, and brightness is often a good way to figure out mass. Most of the time, the black hole was doing the work of billions of suns, making the galaxy look bigger than it really was. like a flashlight stuck to a candle. The remaining galaxies fit the expectations of the standard model after those little red dots were taken out of the sample. The person who worked with Chorowski, Stephen Finkelstein, was honest about it. Based on the usual model of the universe, there is no chaos, he said, at least not from the galaxies. But that wasn't the end of the story. There were about twice as many large galaxies left after taking out the little red dots as the standard model predicts, but not so much that the model breaks, just enough to bend it. Chorowski said that stars might have formed more quickly in the beginning of time than they do now, that the denser conditions right after the Big Bang made it harder for gas to leave while stars were being formed, which sped up the process. Even though this makes sense, it means we still need to change how we think galaxies formed. Webb found something else early in 2025. In the first 2 billion years of the universe, there was a huge circular galaxy that was quickly called the Big Wheel. It takes time for spiral structures to form. It needs growth that is mostly calm and organized, not the chaotic merging you'd expect in a young universe. One of the scientists at Swinburne University of Technology who found the galaxy, Themia Nanayakara, said that the galaxy either put together its mass in a very neat way or formed most of its stars without the violent collisions that usually happen when big galaxies are being made. Either answer goes against what most people think. That same time, another group at Cambridge used Webb to look at more than 250 galaxies from that time and found the opposite trend. Most of them were clumpy, turbulent, and chaotic systems that hadn't formed into smooth disks that could spin. So, in the early universe, there were both messy young galaxies and at least one very mature spiral galaxy at the same time. It doesn't make sense that way. The basic model works smoothly, and none of this talks about the galaxies that are stretched out. Alvaro Po led a study that came out in late 2025 in Nature Astronomy. It included experts from MIT, Harvard, and Taipei. The study found that many young galaxies seen by Webb look incredibly stretched out, like cosmic cigars. The cold dark matter model, which is the basis of standard astronomy, doesn't agree with these curved shapes. They do, however, fit what other models of warm dark matter and wave dark matter say will happen. In these models, the filaments that make up the big structure of the universe are smoother, which lets gas and stars flow along them in long streams. It's more important than it sounds to make that difference. There are more parts to the usual model than just cold dark matter. The scaffolding is it. It decides where galaxies form, how they group together, and how the universe's structure looks at the largest sizes. The cold model assumes that dark matter particles are heavy. If they are lighter or behave differently, that would have an effect on almost every statement that cosmology makes. It would change how heavy galaxy groups are. It would change how dwarf galaxies are usually spread out around bigger galaxies, which has been a source of worry for years. It would change how light is bent around big things by gravitational lensing. The walls of a house won't stay where they are if you change the foundation. What does this mean for us now? The normal form is still alive, not even close. It still gives a very accurate explanation for the cosmic microwave background. It guessed how much hydrogen and helium would be in the universe. It explains why galaxies are grouped together over billions of light years. It has a track record that no other model can beat, but cracks are appearing that weren't there 10 years ago. The Hubble strain won't go away. Galaxies that are bigger, more structured, and stranger than imagined are being made in the early universe. It's possible that dark matter, which makes up about 27% of everything, is not what we've been thinking about it as for the past 25 years. We still don't know what dark energy is or how to measure it directly. It's just a name for the 68% of the universe that is speeding up its growth. Most people don't know about a second, less important conflict. It has to do with how clumpy the universe is and is called the S8 stress. The normal model says that there will be some clustering in the way that matter is spread out in space. Astronomers always find a little less of that grouping than the model predicts when they measure it directly. Adam Rees has said that it is like the Hubble tension's little brother or sister. Not as exciting, but still worth watching. If it turns out that both problems are real, they might be signs of the same problem. There are two cracks in the wall. As he often does, Adam Rees put it carefully in December 2024. The difference between the rate of growth that has been seen and what the standard model says should happen suggests that our knowledge of the universe may not be complete. Now, the results of two of NASA's most important telescopes agree with each other. We need to pay attention to this issue. The amazing thing about this time in astronomy is that the worry is useful. No one is in a panic. The general mood is more like when you've been putting together a jigsaw puzzle for years. Sure, you got the picture right, and then you find a piece that doesn't go anywhere. It doesn't mean the problem is wrong. That means the box picture might not show the whole story. There will be new instruments soon. Wide field scans will be done by NASA's Nancy Grace Roman Space Telescope in order to study dark energy. The Euclid project from the European Space Agency is already making a map of the universe's shape on a scale that has never been done by a telescope before. As more data from the Gaia Space Telescope comes out, scientists will be able to calibrate Cepheid distances with geometric accuracy. This will get rid of another possible source of error. The Atacama Cosmology Telescope has already made the most thorough map of the cosmic microwave background that has ever been made from the ground up. This slightly raises the Planck estimate, but not by enough to close the gap. We are living in a question. This is the most accurate picture of the world ever taken, but it's also telling us two different things. And it looks like both of them are right. That 14 billion years between the beginning and now are filled with events that we have never seen directly. These events are doing something that we don't understand. Some element we haven't found yet. Some process we haven't thought of yet. Something about space-time that we haven't thought of yet. This is where cosmology has been before. In the 1990s, a different contradiction almost brought the field to its knees. There were measurements that showed the universe was younger than its oldest stars. That didn't make sense. That thing the stars lived in was too young for them to be. At that point, it was found that dark energy was speeding up the growth of the universe, which made everything clear. The flaw that looked like it would kill them turned out to be the outline of something huge that no one had seen yet. That's the thing about physics problems. They make me think of ends. Most of the time, they turn out to be doors. You would see a species on a small rocky world orbiting an ordinary star in the outskirts of a medium-sized galaxy if you could stand outside of time and space and watch this. Arguing with mirrors and math about whether reality is growing 6% faster than it should be and getting really mad about it. That's either crazy or beautiful. I believe it could be both. It is not a fail. In all honesty, it's the opposite. When a science hits the edge of what it knows and keeps going, this is what it looks like. There is no damage to the world. That's all the map we have of it. Also, the next version will be both weirder and more beautiful than the ones we've already made. Glad you watched, and see you in the next one.